Y'all are ready? I'm ready.
Yeah, it looks like we're all here.
Okay.
All right. Well, if we're ready, I'll go ahead and kick off some questions for you.
Sounds good.
You guys are obviously familiar with the conditions at Spaceport America, but I want you to go through a little bit of a thought experiment because we're not actually able to launch in the competition this year. So let's imagine that you're carting your rocket up there to Spaceport America and you are assembling the rocket, following the procedures you developed. What goes wrong and how do you overcome that while you're out there preparing things for flight?
Well, I think we can actually speak a little bit to that. We actually had a test flight back in March and did face a number of challenges as we were going through it. The most notable one is, I'll probably hand off to David here in a second as he was a big part of it, was that we actually had a wired connection break, a soldered connection break while we were on site. And basically what happened is our avionics lead, Thomas, actually had a soldering kit in his truck and a wired connection. So we were actually able to wire on site. And David, do you mind expanding a little more on what had happened?
Yeah. So I'm assuming during transport, when the rocket was in the truck, it got shaken around a little bit, and it knocked one of the solder pins off. And so it was still connected, but you have to position it just right for the pin to make contact with the actual board. So fortunately, we did have that soldering kit. If it wasn't available, we'd probably just tape it down so it's stuck in place during the launch.
Yeah, it was, for reference, it was for our air brake section. It was I believe the power supply connection that had failed. And so you could audibly hear the servos that had actuated the air brake system turning on and off for some reason. But luckily we had the soldering kit. Thomas had his truck, which had an outlet basically, and we were able to fix it there on site. Whenever we're going out to site, we try to envision that we're basically trying to bring the shop with us, just because anything goes wrong, just like then.
No, that's true. And now I want you to consider, okay, you've launched your rocket, and what is your most likely failure mode during the flight? What goes wrong and what are the consequences?
So there are a few failure modes, and I'll probably hand these off to the respective leads who are familiar with them. The first one being a CATO, of course, right off the pad. Another one being a failure of the air brake system, and another one would be the failure of the recovery. So for a CATO, I'm probably going to hand that off to Adam. You have a little experience with that. Sorry.
You brought up an old story. So as far as CATOs go, obviously it's waiting to clear, making sure everything's safe, making sure that no one's in the vicinity of danger when that CATO does go off, depending if it's on the rail or in mid-flight. From our experience, we had a rocket on our very first year decide to go CATO about 3 seconds into the flight. So it's waiting for that motor to come down, waiting for everything to kind of fall, any shrapnel, making sure that if we have any carbon on the rocket, any carbon fiber, that we give it time to settle to the ground so we're not walking in a haze of carbon fiber filaments everywhere. And it's taking the proper precautions, getting fire on site, making sure that if their motor's burning on the ground, we're not burning a bush and causing a wildfire in that process. So it's a lot of safety precautions in that step and making sure they're done and executed properly and quickly so that no one gets hurt and nothing else gets damaged in that process. And from there, we can move on to our next, which would be the air brake failure, which Scott and David can talk more about.
Yeah, David, you want to take this one?
Sure. So the air brake system, if it doesn't open as planned, nothing negative really happens. The rocket will just function as normal without an air brake system. It would just the rocket would just reach a higher altitude than intended, because the air brakes don't deploy and they don't reduce the speed of the rocket. That's about it.
Oh, there is one more mode right off the pad as well as at max Q. The servos that we actually used are just barely strong enough to deploy at the expected altitude. We're anticipating, I want to say it was about 10 to 15 pounds per each flap. And we had expected that at max Q or just off the rail, it's somewhere around like 40 or 50. And just based on actual testing we did by attaching a weight to the lever arm of the servo, we were able to figure out that these servos just purely weren't strong enough to open at that velocity. And then I'll probably hand off the last section to Alex for our recovery failure modes.
Yeah, so obviously one of the main possible failures of the rocket would come through the recovery. This year, it would have possibly been more likely that there would be a failure since we were experimenting with a CO2 ejection system. However, everything went there with the deployment went flawlessly. The drogue deployed at apogee, was coming down the main chute. The charge went off, it separated the rocket, but then we did have a failure which was more of a user failure. The way that we had secured the shock cords didn't allow for enough space for that parachute to fully pull out of the body tube. So our main chute got stuck in the body tube. We hit the ground at our descent velocity of that drogue chute. But that would be the main failure for the recovery system with that CO2 charge.
Yeah, I remember seeing that in your video.
Yeah.
And so my follow-on question to all of this discussion of what could go wrong is for next year's competition, which hopefully we'll all get to be out there in the desert and launch things. How do you intend, whether it's you yourselves or a follow-on team, to ensure that the lessons you learned this year and the designs you created are transferred to next year's team in order to be successful?
So I think Dalton and I can probably take over that. Dalton is my project manager for next year. We just went through our elections. Adam Flores is my current project manager. Dalton, do you want to talk a little bit about that partner program that we were setting up?
Sure, yeah. So for next year's program specifically, we're due to COVID and all the complications we've had with that, we haven't had a very big influx of new participants into our program. And so next year we're trying to make a partner / mentorship program where each of the respective leads of a sub team will have select freshman or new incoming person that they teach all their knowledge to, that they basically will help them with all of the processes that go with that sub team, so that they have the knowledge they need to continue on making the team better and learning from mistakes as well.
And if I may toss in a little bit more about what we tried doing this year documentation wise, we documented far more than we ever have in any previous year, whether it be numerical values, actual CAD models, and drawings. We actually have a written list of everything that needs to be updated. We've redlined a lot of our locations that had problems or we had manufacturing issues with. And so a lot of what we have documented now will be able to be transferred to those new members as well. And we can use those as references for that partnership program that we talked about.
That's very good. It's my main set of questions. Mark or John, do you have anything to add?
No, I do not. Documentations is like always vital because you never know what's going to happen next year, and that's great like that.
Thank you.
This is Mark. Noticed in your report you used a scale model air brake. Did you have any prior experience on scaling and comparing units and what your expected values were?
So as far as prior experience goes with that half scale, it's definitely a novel idea for us. The way we looked at it is definitely, at least from a physical component aspect of just applying that 2-to-1 scale. It was very hard to interpret the differences, I guess, in velocities and trying to scale it coming from that aspect. But we were really looking for those flights just to verify that the rocket was still stable. And so we were just looking at it in terms of the static margin and the relationship in the rocket, not so much as the velocities and accelerations that it underwent.
Okay. And as far as team members, do you feel that all team members were equally utilized, or do you think some were overworked and some others were underworked?
Yeah, there was a decent split among the different sub teams. So there was a dedicated member for each of the sub teams. Of course, I have my sub team leads here with me. But as far as being overworked and underworked, we never asked anybody to come in if they didn't have time. In my video, I mentioned the payload not being a part of the series competition, and that was on the basis of going virtual, us just wanting to test the air brake system, and a bunch of my members citing that they would prefer to focus on school. So I definitely, especially going through this pandemic, wanted to make sure the members were able to keep a balance. But there were times during crunch phases, just before test launch or just before progress reports or technical reports, that there were some extra hours, I should say.
Right.
But it was at least a decent split among the different team leads as far as the workload goes.
Good. Great job.
Yeah, we certainly hope you'll be able to come, to the Spaceport America Cup in 2022, I guess it'll be. We'll have a successful launch then. But is there anything that you feel you might not have gotten a chance to express about your project or program and would like to use this free-form discussion to tell us a little bit more about it, something that you think we should know as we're judging all these different teams?
I would say our use of trying so many novel ideas in 1 year. We tried a lot of new things for our team that we had never done before, and it was a lot of experimenting, a lot of risk taking, and trial and error that we had to go through. The air brake system being the biggest one. That was the most manufacturing of metallics we've ever done before on the team. It was the most complicated system I think we've ever done. And it took definitely the most time out of Scott, David, and myself, and a lot of other members to really get that project finished by this year in the time scale that we had put it in. And that doesn't go to show on top of the CO2 system we did for the first time. A lot of our manufacturing processes got updated this year and really made it more of an efficient workspace for all of us. And so a lot of what we had done this year was just new to us. And for next year, we learned a lot of lessons, especially with the air brake and payload system configuration. We had a small hiccup where we didn't realize how to properly set those two together. So for the following years, we definitely have those errors documented, and we're very ready to fix those in the following year. Scott, do you have anything else to add to that?
Yeah, no, I mean, the turnaround time for that air brake system, honestly, I probably would have preferred to have gone longer. I mean, we had been developing it over the past year and a half. It was originally a pet project of one of our senior members who has then transitioned it over to David here. And I really like that process because, one, it got new members involved in an older project to be able to iterate it, improve upon it. And I'm really hoping that future teams are able to do the same thing. I mean, just working with this full-scale air brake system this past year, I can already see so many problems with it. The vortices it creates as it's going through the vehicle, the location of it, I'd much rather have it close to our center of pressure. Just a number of things that I just feel can be improved upon. I want to make sure that the next person over is able to implement those, and that goes along with that documentation idea we mentioned earlier. But as far as like concerns for other teams, I would like to note that including so many novel ideas isn't a bad thing in terms of just trying new things, but it's the magnitude of them that makes it difficult. So having longer development periods is a-okay. Having patience when it comes to these projects is a-okay with me. It definitely felt rushed a little bit at times this year. Actually, Anita, is there anything you wanted to add to that? Because I know you always have some thoughts about this.
So last year I was the lead engineer, and under me we started the air brakes, and with launching our original project we were at Spaceport. We did it in September, and this gave a lot of ways to Scotty's team and this year's team, and just that transition and the learning and the testing that we keep doing no matter what is going on is the true definition of this team. We learn from our mistakes, and we're always in that shop and ready to pound it out, and we work great as a team, and I hope that's the legacy of the Atomic Aggies as me and Adam do leave, and we want to keep with Ezra and the team and see what happens in future competitions. I really think that's just the legacy that we're trying to leave behind, not just our manufacturing skills or our knowledge. It's not just us, it's the teams that come after us, not just next year, like 6 to 10 years later, hopefully.
Mm-hmm.
Do you gentlemen have any other questions for us?
I don't think so. I think we're probably need to be moving on to our next group to judge. So thank you all for your time.
Absolutely. Thank you.
Thank you for your time.
Yes,
Have a
thank
good
you.
day.
Thank you. It was great. Thank you.